Welcome to Chapter 10, 10.1. I'm going to move quickly here as we review some parametric equations and some calculus to go along with it. From your notes, hopefully you're looking at your notes right now. Example 1, the C is a curve, and that's described parametrically, where x is equal to 2t, y is equal to t squared minus 1 on the given domain that you see here. To go slowly here, what we're going to do is make a chart. So we're going to have select values of t, and for each one of these select values of t, we're going to find the Cartesian point. So I'm picking from -1, and I'm going at a step size of 1/2 to get these values. For each one of these t values, we'll find the corresponding x and y values. So at -1, x will be -2, and y will be 0. At -1/2, we have -1, -3/4. At 0, we have 0, -1. 1/2 is going to be 1, -3/4, and so on and so forth. 2, 0, 3, 5/4, and 4, 3. Now we are going to graph this. If you have your notes, then you have some graph paper on it. I'm just going to do it on a real crude scale. All right, so I'm going to plot the points. -2, 0, -1, -3/4, 0, -1, 1, -3/4, 2, 0, 3, 5/4, and 4, 3. Okay, now we're going to connect these dots with a smooth curve representation, and it stops at these endpoints because of the restricted domain. And there we have it. Now the AP questions may ask for the orientation of the curve. Now when t was at its leftmost point, we were at this endpoint here, and then it progressed in this fashion, left to right. So we use the arrows to show how the curve is scribed out, if you will, as t progresses. Next, so that was actually part A. So next, part B wants to find dy dx. So dy dx you should know as the slope, the Cartesian slope of a tangent to the curve. And that's exactly what's going to represent here, the Cartesian slope to the curve. The problem is it says dy dx. We desire dy dx, but in terms of t. So we're going to write this employing the chain rule, dy dt over dx dt. And that's a formula you should memorize, but also understand. See, multiplying the reciprocal, the dt's cancel out. Anyhow, to do this, we're going to do the derivative of y with respect to t, and that's 2t. And the derivative of x with respect to t is 2. Simplifying that comes out to be t. So the slope of the tangent to the curve is always equal, in this case, t. That's pretty interesting, actually. In part C, it wants us to turn this parametric equation into a Cartesian equation. So the most simple way to do that in this case, we recognize that x is equal to 2t, which tells us that t is equal to x over 2. And we're going to take that and plug it in for what we know as y. So we have x over 2 squared minus 1. So y is equal to x squared over 4 minus 1, the parabola. But the problem here is if I just saw this parabola, I wouldn't know that it is the parabola here, so we need to adjust the domain and range. So I'm going to talk a moment about how to do that. For the domain, we see that t is between -1 and 2. We can multiply t by 2 to get 2t, and that will make this 4, and that will make this -2. And 2t, the reason we did that is because that is what x is. So x is between -2 and 4, and we can see that in the graph. A similar logic can be employed to find the range. T is between -1 and 2. T squared now is greater than or equal to 4. Careful here, you don't want to just square -1 and say 1, because there are fractional values that are, when squared, smaller than 1, but still bigger than 0. Lastly, if I take t squared and subtract 1 from all sides, then I get the range. And the range can also be seen in the graph. In example 2, we're going to look at a couple things. First thing, let's take a look at what this might graph as. As we go forward, you should, if you don't already, you should know what this shape would make, this curve C, which is defined parametrically as you see in front of you. Let's do this without writing. We're going to plot some values of t. So if I plug t equals 0 into the equation, and I have this all wrong. That's not what it says at all. It says that x is equal to a cosine t and y is equal to a sine t. There we go. Anyhow, let's plug t equals 0, and this makes this a times 1, which is a. So I'll locate this point at a. That's also true because when we plug t in here, 0 and for that, we get a times 0, which is 0. So a on the x, 0 on the y. Next, let's plug in pi over 2 for t. So x is going to be a times 0. So the x will be 0, and the y will be a times 1. So we are here, a. Keeping going, if I plug in pi, it's going to come out here. If I plug in 3 pi over 2, it's going to come down here. And my circle is being scribed. Now, this is the worst circle I've ever drawn. But my circle is being scribed counterclockwise. So I'll put my arrows here to show the orientation. As t increases, we form the circle. So you should know that this parametric equation is the equation of a circle with radius a. We can also show that when x squared plus y squared, when we do that expression, we get a squared cosine squared t plus a squared sine squared t. We can factor out the a squared, then we have our identity, cosine squared plus sine squared equals 1 equals a squared. X squared plus y squared equals a squared, the recognizable form of a circle with radius a. The original question does not ask for, but I'm going to do this. I would like us to find dy dx. So again, that's dy dt over dx dt, which will yield, let's see, what will that yield? A cosine t over negative a sine t, and that will simplify to negative a cotangent of t. So dy dx, the slope of the tangent to the circle in this case, is always equal to negative cosine of the value of t. In example 3, x equals negative 2 plus t squared, y equals 1 plus 2t squared. We're going to plot some points here to figure out what the shape is. So t is the element of the real, so I'm going to start off with some negative values, increase, get some positive values, so that we get a picture of what this is. So when I plug in negative 3, that's going to give me 7 for x, and it's going to give me 19 for y. Plug in the negative 2, and that's going to give me 2 for the x, and that's going to give me 9. And finishing them up, we get those points. We plot those, you're going to see that at negative 2, 1, we have a point, and then this progresses linearly, pardon my lack of scale, and the line keeps going. The problem is this is not truly a line. If I ask for the geometric shape, it's actually a ray, because we never can go beyond x equals negative 2. So there it is, a ray. Now to indicate the orientation, if we keep going back negative t's, negative 10, it's actually coming from up here, so it's going to come down like this, and then boom, it's going to bounce off, and then it's going to go back out into space. And the Cartesian equation, if I solve for t squared, then t squared is equal to x plus 2. We're going to substitute that in, and we have 1 plus 2 times x plus 2, or y equals 5 plus 2x. That's the linear equation that I have graphed over here. This again is restricted. Let's look at the domain. So t is an element of the reals. T squared then is greater than or equal to 0, and negative 2 plus t squared is greater than or equal to negative 2. That is our x. So you can see if we restrict the domain of this line, we get the ray that is present in the graph. And then we can find dy dx, dy dt on the top, dx dt on the bottom, and simplifies to 2, which makes perfect sense because that's the slope of this line or ray portion of the line. Now please keep these 3 examples ready, because in the next video we're going to refer to them after we talk about some concepts. We'll go back to these examples and perform some different calculus manipulations.